Continuity. A function is said to be continuous if there are no breaks, jumps, or holes on the interval being considered. Generally, when graphing a continuous function, we say that a function is continuous if you can draw it without lifting your pencil off the paper. The mathematical definition for continuity is a function f of x is continuous at x equals c if f of x is defined at x equals c and the limit as x approaches c of f of x equals f of c. So what that means is we're going to have something that's continuous if as we approach the value in the independent direction, the limit is equal to what we would get if we plugged that number directly into the function. So let's look at just a couple quick pictures of graphs that are and are not continuous. So if we're considering a function that's continuous, you may have something that looks like this. This function can be drawn without lifting my pencil off the paper and has no jumps or breaks or holes. An example of some discontinuous functions are piecewise functions that jump. So here we have a jump with a hole, or have asymptotic behavior. So here we can see a couple places where this function is discontinuous. So mathematically, if we want to show that something is continuous, we're going to use the definition. So let's go ahead and look at a couple of examples of how we'll study continuity on different functions that we'll look at in this class. Example 1. Use the definition to show that f of x equals 3x squared is continuous at x equals 1. Using the definition means that we need to show that the limit as x approaches 1, remember that's where we're interested, of 3x squared is going to be equal to the functional value at 1. That's our mathematical definition. So to show what the limit as x approaches 1 is, we need to consider the limit as we approach 1 from the left and the limit as we approach 1 from the right. So when we approach 1 from the left, we're considering values like 0.9, 0.99, 0.999. When we plug those into our function, we get the following values. We get 2.430 for 0.9, 2.940 for 0.99, and 2.994 for 0.999. So again, I want to consider what these values are approaching as I take the limit as x approaches 1 from the left. And so here, I feel confident in saying that these values are approaching the number 3. I want to do something similar to the right. I want to plug in 1.1, 1.01, and 1.001. When I plug in those values, I get 3.630 for 1.1, 3.060 for 1.01, and 3.006 for 1.001. So now, when I consider the limit as x is approaching 1 from the right, I can confidently say again that this is going to be approaching 3. So the limit as x approaches 1 from the left is the same as the limit as x approaches 1 from the right, which is 3. So the limit as x approaches 1 of 3x squared is also 3. So my question is, does that match the functional value? If I were to take 1 and plug it into my function, I would get 3 times 1 squared. Well, since 1 squared is 1 and 1 times 3 is 3, my functional value also equals 3, which means that this function is continuous at x equals 1. So that's how we use the definition. Now, most of the time that we're talking about continuity, we're not going to be doing it so formally. Instead, we want to get a good feel for whether or not we think something is continuous and look for signs that a function may or may not be continuous. So let's go ahead and try the next problem. Example 2. Determine where f of x equals 2 divided by x minus 4 is not continuous. So looking at this function, the first red flag I see is that in the denominator I have an x minus 4. I know that I never want to divide by 0, so I'm concerned about the number 4. So I'm going to make a note over here. Now, any other number I can think of, 0, 1, 5, 12, I can plug those all in confidently, and I know I can get a functional value. So there's nothing else on my radar that might be a red flag. If I consider the graph of this function pictured below, I can see that at 4, something really interesting happens. I get what's called an asymptote. So again, if I want my function to be continuous, then I need the limit to equal the functional value. Well, I know that there's not even a functional value that happens at x equals 4, so I know I can't be continuous there. But I can also support that with my limits, because if I consider the limit as x approaches 4 from the left, I am approaching this asymptote that shoots down to negative infinity. And if I look at what's happening from the right, it shoots up to positive infinity. Neither of those are approaching a functional value, and they're certainly not the same. So this function is not continuous at x equals 4. But everywhere else, I can see, both on my graph and through my testing, that the functional values will be the same from the left and the right. So any other point I pick that's not 4, I should have no problem, because the limit will match the functional value. So again, my intuition told me that I don't want to divide by 0. And then when I graphed it, it confirmed what I thought, because I saw this asymptote. And so I couldn't draw my graph at 4 without picking it up off the paper. So here, again, this function is continuous everywhere except for 4. Example 3. So let's take a look at a piecewise function. We want to determine where the following function is continuous. So we have x squared minus 4 if x is less than 0, and x minus 4 if x is greater than or equal to 0. So when we think about these functions, x squared minus 4 and x minus 4, there's not a whole lot of concern. We don't have anywhere that we're worried about plugging in any values. We don't have any denominators that might equal 0. We don't have any square roots here that might end up with something negative underneath. So we're not so worried about jumps and holes and bumps. However, because it's a piecewise function, we always have to worry about a jump happening right where the function is split. So here, my function splits up at 0. Okay, so when x equals 0, I need to determine if the limit is going to be the same from the left and the right. So if I look at this graph and I look at what's happening from the left, my x squared minus 4, as I approach from the left, the y value is going to equal negative 4. So the limit as x approaches 0 from the left of my function is going to equal negative 4. And again, when I'm approaching from the left, I'm considering x squared minus 4, because that's the function I consider when x is less than 0. If I take the limit as x approaches 0 from the right of f of x, well, now if I'm bigger than 0, I'm in the x minus 4 situation. And if I look at what's happening on the graph here as I approach from the right, that also looks like negative 4. I could confirm this by plugging in a couple values less than or greater than 0 into each function, and I will see that they both indeed approach negative 4. So since it's the same from the left and the right, then the limit as x goes to 0 of the whole entire thing equals negative 4. So we're going to be continuous here in terms of the limits, but we also have to make sure that that's true in terms of the functional value. So we know that the limit is negative 4, but I also need to know what happens when I plug in 0 into my function, just to make sure it's continuous at 0. So if I plug in 0, I need to go to the equals case, because that's the case that includes 0. So if I plug a 0 into the equals case, I get 0 minus 4, which also equals negative 4. So the limit is going to equal the functional value, and therefore is continuous at 0. 0 was the only place that I was concerned about. Looking at the picture, I can see there's no other discontinuities that I have concerned about. So here, this function is continuous everywhere. It turns out that most of the functions that we're going to study in this class happen to be continuous wherever they are defined. So these functions include polynomials, so that's your x squared, your x cubed, things of that sort. Exponentials, so e to the x, 5 to the x, 10 to the x, sine and cosine. Additionally, functions that are created by adding, multiplying, or composing continuous functions are also continuous. So that's really helpful because if we can figure out where these types of functions are defined, that will also tell us where they're continuous. And we talked about where they are defined by talking about domain in the first section that we studied. So for example, on what intervals are the following functions continuous? So the first one is sine of x. So if we can consider where it's defined, then we'll know where it's continuous. So sine of x is going to be defined for all x values. All real numbers can be plugged into sine x without any problems. That's the domain. Therefore, it's also going to be continuous for all real numbers. So from negative infinity to infinity, sine of x is continuous. Similarly, x squared plus 1 is defined for all numbers. The domain here is all real numbers. Therefore, it's continuous for all real numbers and continuous from negative infinity to infinity. The third one, the natural log of x, that wasn't on our list. However, it's also a function that's continuous where it's defined. So we have to think very carefully about where the natural log of x is defined. If you don't know, it's worth it to graph it on your calculator and see where you think it's going to exist. But I will tell you, the natural log of x does not exist for negative numbers and is not defined at 0. So the natural log of x is only defined for x values greater than 0. That means it's also continuous only when x is greater than equal to 0. So we can write it like that, or we can stick with our other notation and we can say 0 to infinity. I'm using open brackets again because I'm not including the endpoint of 0. So the natural log of x is only continuous for x values greater than 0. For the next example, we're going to look at something that's not as continuous as other functions we've studied in the past. Instead, it's going to be discrete in nature, and so we have to consider where it's going to be continuous and where it won't be. So consider a pay-by-the-hour parking garage. Any fraction of the first hour is $8. So as soon as you pull in, you're charged $8, and as long as you leave by the 1 hour mark, your fee is $8. However, as soon as you go 1 minute over the 1 hour mark, the price jumps to $16 for the second hour. So minutes 61 through 120, and then $24 for hour 3, and so on and so forth. So it's $8 for each additional hour, but it stays that fee for the entire hour. So if we're talking about the continuity of this function, we have this piecewise function that we can sketch out to see where it's continuous and where it's not. So here, we're going to plot the price versus time in hours. So we can get a good idea of what this is going to look like by graphing what the price is going to be for each increment here. So we know that for the first hour, it's going to be $8 all the way up until the 1 hour mark. But then the price is going to jump to 16 for any amount of time over 1 hour. So we're going to put a hole there because right at the 1 hour mark, it's still $8. And then all the way up to $2. And then all the way up to 2 hours is $16. And then we jump to $24 for 3 hours. And then we're going to jump up to $32 if we stay more than 3 hours. So we have an open circle here, all the way up to 4 hours, and so on and so forth. So this is what's called a step function. It's a piecewise step function. And we can see that we get these discontinuities at the hour marks because that's where we get these jumps, right? And they would just continue going on and on forever and ever. And so we have these small intervals where this function is continuous, but we have a lot of places where it's not. So in terms of where this function is continuous, it's going to be continuous from 0 to 1, not including the 1. It's going to be continuous from 1 to 2, but not including 1 or 2 because we have these jumps. We're going to be continuous from 2 to 3, but not at 2 or 3. and then from 3 to 4, so on and so forth. So on these little intervals between the hour marks, then we're going to be continuous. However, we're not continuous at the integers where we're jumping from either nothing up to 8 or from 8 to 16 because we have these jumps. So we're continuous on the interval, but we're discontinuous at 1, 2, 3, 4, 5. So here again, this is called a step function, and it's an example of a real-world situation where continuity fails for the most part. Okay, so let's talk big picture for a minute. Why is it important to study the continuity of a function? Well, understanding whether or not a function is continuous is important in understanding the variability of a function. We want to know how temperamental it is. How likely is it to change? What sort of impact will it have if I make small changes in what I'm doing? So a function is continuous, such as 2x plus 1, then a small change in the independent variable is likely to produce a small change in the dependent variable. And it's also going to produce a predictable change. So if I were to go from x equals 1 to x equals 1.01, then my continuous function output is going to change from 3 to 3.02. So it's a small and predictable change because it's a continuous function. Now, if you think about the garage and pay example, which was not continuous in general, then a change from 1 to 1.01 results in a huge output change, right? We jumped from $8 to $16, which was a much larger jump. It's considered volatile. We like functions that are continuous because when we study calculus, one of our goals is to be able to use what we know about the function to predict what will happen later. And in order for something to be predictable, we need it to not be hugely variable or volatile. So we mostly study continuous functions, and we try to model with continuous functions in calculus because then we can use it more reliably to make predictions of things moving forward.